Okay, sorry about that. So let's start with this example problem here. So keep in mind we're going to look for an initial value, the amount that we start with, and then we're going to look for our rate of change, that ratio that describes how things are changing. So we're going to find the way that the graph represents these parts of the function, and we're going to look at how to write it in the equation and write the rule. So Josie has 1.5 cups of water in her watering can. So right off the bat, we notice an amount, and it's constant. This isn't 1.5 cups of water per day or anything else. This is a constant amount, and this is what we're starting with. So this is going to be our initial value. Which, remember, on our graph is going to look like our y-intercept. So as we look down on our graph, we can see this point on the y-intercept that's at about 1.5. So we have 1.5 cups of water in the watering can, but then Josie fills the can before watering her plants. So she's adding to it, and as she does, the water flows into the watering can at a rate of 1 cup every 4 seconds. So here we have a rate, which, remember, is a comparison of two quantities. So I could write this as 1 cup per 4 seconds. And when I write it as a fraction, it looks an awful lot like rate of change or slope. So this is the rate at which my function is changing. 1 cup every 4 seconds. So that's my rate of change of the function, which means it's also the slope of my line. But let's look at our graph to see how this looks on the graph. Because when I'm given a linear equation and I want to find the slope, I have to find 2 points on the line and I have to count out the slope, the rise over the run. So this looks like a good point because it looks like it crosses at exactly 2, 2. And as I follow the line, it looks like this is another exact point. This is at 10, 4. So from this point to this point, I can count my rise over my run. So I'm starting at 2 and I'm rising to 4. So that's a rise of 2. And now I'm going to run 2, 4, 6, 8. So if I'm thinking of my slope, or my m, as my change in y over my change in x, or my rise over my run, I'm rising 2 and running 8. And I know that I can reduce 2 eighths down to 1/4. So that's how I see 1/4 reflected in the slope of my line, and 1/4 is going to be my rate of change in my function. So I'm going to see that in the equation that we write. So looking now at our graph, we already said that our initial value is 1.5. And we're looking at our graph and seeing that our y-intercept is also at 1.5. So now that I have those two pieces of information, I can use those to write my function rule. Remember, my equation says y equals mx plus b. M is my slope, or my rate of change, and b is my y-intercept, or my initial value. So when I write this equation, I'm going to say y equals, I'm going to replace m with 1/4, and I'm going to replace b with 1.5, and it's positive, so I can put plus 1.5. So that's what those components look like in the rule from a word problem and in the graph. That's how they all relate together. So now it is your turn to try one. Let's look for the rate of change and the initial value for the function in this graph here. So as we're looking at this, I'm noticing one thing right off the bat, and that's that this line slopes down from left to right. So I'm looking for a negative slope or a negative rate of change. So as I am finding that value, I'm going to pick this point because this has an exact location on my graph. And I might pick this point right here. So I notice that my scale is counting by twos on my y-axis. So this is 2, 4, 6, 8. But I'm counting by ones on my x-axis. So I need to be careful when I'm counting the rise and the run. So from this point, I need to rise -2, and I'm going to run +1. Rise -2, run +1. Rise -2, run +1. So my rate of change, or my slope, is -2 over 1, which I could simplify and just write as -2. My initial value then is when x equals 0. So that makes my initial value +8, and that's going to be my y-intercept. That's the point where my line crosses the y-axis. So that's at +8. So now if I use y equals mx plus b form, I'm going to put -2 in for m, and I'm going to put 8 in for b. So my equation becomes y equals -2x plus 8, and that's my function rule right here. I'll write one more example, nope, two more examples. The linear function in the graph models the height off the ground in feet of a person riding a zip line t seconds after pushing off from the platform. And we say t seconds because that enables us to look at any number of seconds that we want to. Half a second, 1 whole second, 2 seconds, 20 seconds. So t just stands for any number of seconds that I want to look at in this function or on my graph. So we're trying to figure out how high off the ground is the platform. Well, as I think about the different parts of a linear function, I know that after 0 seconds, I'm still going to be on the platform, right? So if I want to know how high off the ground the platform is, then I'm looking for my initial value. Because my initial value is going to tell you where I'm starting from. So on my graph, that would look like my y-intercept. So as I look at my graph, I see that this linear function crosses the y-axis at 100. And I know that my y-axis is measuring height in feet, so 100 stands for 100 feet. I also know that my initial value in an equation is the b, y equals mx plus b. Now notice I'm using different variables, but h is replacing my y and t is my x. I'm just using h for height and t for time because it's more specific to this situation, but it still represents the same idea. So I'm still in y equals mx plus b form. So b is my initial value, and I can see that my function rule also tells me that that platform is 100 feet off the ground. Then once I start zipping, after 20 seconds, I'm down to a height of 75 feet, but when I start, I'm on that platform at 100 feet. All right, your turn to try this out. The function d equals 125 plus 80n models the amount of money in dollars. So my D stands for dollars. The Zipline ticket cashier has in her cash register after selling N tickets. So N stands for the number of tickets that have been sold. We're trying to use this linear function rule to figure out how much money the cashier had in the register before she sold any tickets. So before she sold any, that means she's sold 0 tickets. N equals 0. She has sold nothing, but she still has some money in her cash register. If I'm looking for an amount at the very beginning or what I started with, that sounds a lot like my initial value. which on my graph is my y-intercept. So I'm going to take this equation and I'm going to rewrite it so that it lines up a little better with y equals mx plus b form. So I know that d is like my y in this case, and I see that I am multiplying 80 times n, so it must cost $80 to get a ticket to ride the zip line. This better be a good zip line. So 80n is like my mx. This is my slope, this is my rate of change. And what I'm adding to that is this positive 125. So the money that the cashier has in her register before she sells any tickets would be my B, my initial value, my y-intercept, which is $125. And you guys are all set to rock out your 8.3 digits homework. Good luck.